So you might recall the idea of inverse functions from Algebra 2. We're going to talk about it for a couple of days, maybe a little bit of new stuff, maybe a lot if you don't remember it from last year. But let's just go over some vocab that's important. A relation, we've already talked about what a relation is. It's just a set of ordered pairs. It can come in the form of like a mapping diagram, an XY chart, a graph, an equation. It's just like a general term for ordered pairs, okay? And then we know what a function is. A function has no repeat x values, passes the vertical line test, okay, a function. Well, the inverse of a function is switching the domain and range, or the x's and y's. So literally, if you had a table of values with x and y's, the inverse is the flip of that. Just literally flipping it, okay? That's the inverse. And we're going to do it in an xy chart off of a graph with an equation, switch the x and y, all different ways. And when the inverse of a function is also a function, we call it a one-to-one, okay? So here's the thing. I could take a, let me explain it. Okay, so let me try to explain it with these mapping diagrams, okay? So what we have here is a one-to-one function. What that means is f of x, let's just call f of x the original function. It is a function, right? There's no repeat x values. If I flipped these, then this would be my domain and this would be my range. I would also have no repeat x values, right? So basically by looking at this, as long as there's no repeat y values, the inverse is a function, and they call it a one-to-one when the inverse is a function, okay? Look here. This is a function, right? Domain has no repeat x values, but the range has repeat y values. So if I flipped these, this would now be the domain, and this would be the range. So our domain would have, using 4 twice, that would make it not a function. So this is considered not a one-to-one function. The inverse of this is not a function. And this meets none of the criteria. Right off the bat, we are reusing x values more than once, right? There is repeat x values, so this is not a function, so we don't even check it for the inverse, okay? So that's a little confusing. I'm going to explain it best on the next pages. Now, there's something else. There's something called a horizontal line test. So you guys know, like, let me just sketch a quick graph for you. A parabola, right? This passes the vertical line test. A parabola is a function. But is the inverse a function, or is the inverse one-to-one? The answer is no, because this does not pass the horizontal line test. The horizontal line test is, when I do that, I'm touching the graph in more than one place. That means when I flip all of those, I would have repeat x values. So repeat y values in a function means the inverse is not a function. Okay, so it's a little confusing. We're going to see some examples coming up in a second. But let me give you some properties of inverse functions. So if you look at this graph right here, they labeled it for us. This is a function right here. Okay, so whatever, it's graphs and points, it's a function. Then they switched all the x, y values, and they graphed the inverse. And what you should understand is that a function and its inverse are always reflections over this line right here. It's called the identity line, which is y equals x. Y equals x is the parent function of a line. And the reason it's called identity is all the x's and all the y's equal each other. 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, negative 1, negative 1, and so on, okay? And so this is the parent function of a line before we go up, down, left, right, flip, stretch, shrink, any of that. So that's that. All of these points are equally distant from that, all right? And we're going to see that. We're going to do it by hand in a second. And we have lots of ways of noting things in algebra, and this is no different. Inverse is written like this. It's got a little f to the power of negative 1 of x. We call it f inverse of x. Don't let that negative 1 make you think of like flipping anything. It's separate from that. That's just when you see that, like function we usually just call f of x. The inverse would look like this. So you'll see me using that notation quite a bit, okay? So inverse, f inverse of x, or the inverse of x, or however you want to say it. So if the inverse is just flipping the x and y's, fancy word for x is domain, fancy word for y is range, so the domain of a function is equal to the range of the inverse. And the range of a function is equal to the domain of the inverse. Just flipped, okay? So let me try and explain it better with some actual examples. Okay, so here we're going to, William, you okay? You good? Okay. For each of the graphs below, draw the line y equals x. So we're going to draw our identity function. And then we're going to sketch the inverse of the function. And then is the function one-to-one? Is the inverse function is what they mean. Okay? Well, I'll come back to that. So here we have a function, graph for us. Okay? And if I went ahead and put on there the identity function, one way of graphing the inverse, it should be straight. One way of graphing the inverse is to just reflect over this. I find that to be a little confusing. Like I'm good reflecting over a horizontal or a vertical line, but diagonal for me gets a little confusing. So I'm just going to share with you another thing you could do. If we pull some points off of this function, just some random points, just pick a few. Like, oops, I stapled this out of order. To the left 3, down 2, that's this point right here. Maybe 1, 0, that's a point right there, there. And maybe one more, 6, 1. So I just picked like 3 random ones. There's no wrong number, which ones you should pick, okay? And then if I just flip them, literally, just flip the x's and y's, this is giving us the inverse points. And graph those. Okay, thank you. Yeah. Your first grade teacher should have some IDs for you guys. Okay, so -2, -3. See, that's that point reflected. 0, 1. There. And then 1, 6. I think that's right here. I can't see. But something like that. And then you can see how it's the reflection of that point right over that line. Okay? Now this last question is saying, is the function one-to-one? So is our inverse a function? Meaning, are all my x values different? Does my original one pass the horizontal line test? Yes, yes, yes. So yes, this is one-to-one. Okay? There's no repeat x values in my inverse. There's no repeat y values in my original. So that's what kind of gets confusing. Which one are we talking about? Okay? Look at this guy. This is a parabola. This is one we're going to talk about a lot, the quadratic parabolas. Okay? So quadratic graph of a quadratic is called a parabola. So this is a function, right? It passes the vertical line test. Is it one-to-one? No, it does not pass the horizontal line test. We already know that the inverse is not a function. So just because it has an inverse doesn't mean the inverse is a function, okay? So let's just do it the same way we did the other one. So I'm just going to pick a few points off of this, and I already did this. I picked one like from this branch, so -2, 2. I used that vertex, which is 0, -2. And then I got one from the other branch over here, which is 2, 2. So I just picked 3 points off of here. Here. And you guys know there's that. See, to me, that's really hard. I would have a hard time reflecting over that. That's why I like to use this method. And this is the way your homework does it too, so it just makes it a little easier to keep it the same. But that is what we're doing. When we flip these, we are reflecting across this line. So when I flip these, let's see what that graph looks like. So right to down to, -2, 0 would be here, and then 2 would be here. So you can see that when we do the inverse of a parabola, I call this a sideways parabola, okay? That's just my way of naming it. But it is a parabola, it's just going to the side, easty or westy, I call them sometimes too, going to the east or the west. But this is not a function, right? It does not pass the vertical line test. So again, the original function failed the horizontal line test, so that told us immediately that our inverse was not going to be a function. So our inverse, we say, does not exist. Okay? If your inverse is not a function, we say the inverse does not exist. Okay? So just because the function is an inverse doesn't mean it has an inverse function. Okay? And this is a really common one. All right? And we're going to talk about that one more time on the next page. But before we do that, this first example, it asks us to show that these functions are inverses of each other. So if you look right here, sorry, I didn't mean to write a line through it. This is your composition of function notation, f of g of x. Remember, we just took a test and had that on there. We had to put one inside the other. What we're going to say is, if you put the inverse inside the function or the function inside the inverse, every time you do that, if they are inverses of each other, you should get x. Let me put it in English. I have f of x and g of x. What I'm going to see is, are they inverses of each other? Would they do this fun thing here in a graph, okay? So I'm going to do f of g of x, and I'm going to do g of f of x. Any order, doesn't matter which one you do first. I'm going to put one in the other one in the other, and if we get x in both situations, that means they are inverses of each other. So we're basically saying yes or no. So remember how to do this. Starting on the right, we go to the left. So I'm taking g of x, and I'm plugging it into f of x, right there. So that would be 4, parentheses, all of that, plus 3. Simple math, guys. This is 4 times a fraction with a denominator of 4. The 4's cancel. You're left with x minus 3 plus 3. The 3's cancel. We are left with x. That's a good sign. If this one is also x, they are inverses of each other. F of x into g of x. That's this whole thing plugged in for x in the other equation. So we don't really need parentheses because that x doesn't have like a number in front of it, doesn't have a power. So I'm just putting 4x plus 3 in for that x, then minus 3 over 4. 3 minus 3 cancel. 4 over 4 cancels, and we're left with x. So what we just found is that f of g of x equals g of f of x, and they both equal x. So yes, they are inverses of each other. And this is your identity function. Remember, that's the y equals x that goes right through, right? So that's the magic answer there to determine if they're inverses of each other. Okay? Now, tomorrow we're going to get deep into graphing. Deep, deep, deep. Today we're touching on graphing, okay? In fact, there's no graphing in your homework, but for me to make you understand this last set of examples, I have to kind of go over some graphing stuff with you, okay? So I want to talk about parent functions. We talk about parent functions in this class all the time. We've done exponentials and quadratics and lots of things, but there are some, like basically 6 or 7 that you really need to know. And some of them you already really know. So some parent functions are friendly and some are not as friendly. So let's talk about the really friendly ones just to start with. Like, let's start with lines. Lines are the easiest graphs to work with, right? Lines look, and I'm just going to use this space right here to write some notes. Lines are y equals mx plus b, right? It looks like this. Cubics, which we haven't really done a whole lot with, but cubics are y equals x to the third power, and they look kind of like an S. So they kind of look like a line with a little curve in the middle. And the last, sadly, there's only 3 really friendly ones, is the cube root, which is y equals the cube root of x. It looks kind of like a cubic, but it goes sideways. So it makes like a kind of a wave horizontally. What is friendly about these 3 is their domain and range is all real numbers. There's no restrictions. There's no numbers that cause any problems with them, which means when you find their inverses, there's no problem either. Okay, what you're going to start seeing, what I'm going to show you, is there's some unfriendly ones for different reasons, but for most of them, it's because what makes them not as friendly is that there's certain numbers you can't put in the denominator, certain numbers you can't put in the radical, right? We can't have negatives, for example. You can't have zeros in a fraction. So those make the problems a little trickier when you find the inverse. So we're going to talk about that down here, but let's just talk about the unfriendly ones first. And the first one is the quadratic. I mean, it's the one we're probably most familiar with besides a line. But truthfully, they're not really friendly when we're dealing with inverses, right? So a quadratic looks like that. And I already showed you what the inverse of a quadratic looked like. It wasn't an inverse, right? It went sideways. Another one is the square root radical. I don't know. You have one thing added here. I think that's the only difference, right? Here? Okay, don't worry about it. I didn't know that yours was different, but it's not a big deal. I'll explain why in a second. Okay, so radical, because this graph is fine. When you do the inverse of this, you still get a function, but you can't have negatives under that radical, so it makes some things tricky, which I will show you. And lastly, that I want to talk about is the absolute value graph. It's exactly like a parabola, but it's not curvy, it's straight, makes like a V. So these have varying domain and ranges, which makes when you flip it tricky. And I'll show you that right here, show you how easy or difficult this one is and how easy this one is. This is one of our non-friendly ones. This is one of our friendly ones, and I'm going to explain it. So I know you guys have something like this here, right? X is greater than, is that what's on your paper right there? Okay, so I'm going to write it in interval notation. Okay, so let's just talk about this graph. What you are now kind of learning, because I've just talked about it for 5 seconds, is that when you have a radical like that, it's half of a sideways parabola. Half, okay? It's just like the top half, or if it was negative, the bottom. It goes, starts at a point and it goes like that. And we're going to graph it. And you might even be able to make this extension, that plus 3 means it goes left 3 and then down 2. Remember, all of our transformations apply to every single parent function. That's where they're getting this negative 3, is where the range starts, because it goes left 3 and down 2. Now, this is not a graphing lesson, like I said, okay? You don't have to know how to graph this today. We're going to kind of talk about it more tomorrow. But if you wanted to put it in your graphing calculator, which I did for you, it would look like that. So I typed it in here. I graphed it. You could look at the table. But you can see it's like the sideways parabola, and it went left 3, down 2. Okay? And I'm not even graphing it perfectly. It's something like that. That's what this graph is, right? Now, what we're going to do is find the inverse of this algebraically. Switch the x and y, solve for y. So remember, f of x is y, okay? And so I'm just going to switch those variables, but don't forget you still have to solve for y, okay? So we have to get the y by itself. So you're going to do all your algebra 1 tricks of moving things from one side to the other. Remember, I need y by itself. It's trapped under a square root. How do I get it out of there? What? Square it. Right. Opposite of a square root is a square, which is nice. It just leaves us with the radicand, which is y plus 3. But don't forget what you do to one side, you have to do the other. And you don't have to FOIL that. Leave it in the parentheses, totally fine. And then one more thing to get y by itself would be subtracting 3 from both sides. So my inverse, let's use proper notation, the inverse would be x plus 2 quantity squared. When I say quantity, it means what I just said was in parentheses. X plus 2 quantity squared minus 3. Right? This is the inverse. But this is really important. If I just said, hey guys, what does this graph look like? This graph right here, pretend it didn't come from anything else. I think you guys would all know it looks like this, right? That's a parabola. Left 2, down 3, who cares? But it didn't start with all of those points. It started as this graph. So when you do the inverse of something that has a restricted domain and range, I forgot to put the range there, sorry. The range would have been from -2 to infinity, right? -2 to infinity, -3 to infinity. When I do the inverse of this function, I do the inverse here as well. So the domain is now the range, and the range is the domain. So what happens here is we actually are going to the left 2, down 3, and then it ends up being half of a sideways parabola. You can't all of a sudden have all these extra points, of a full parabola like this, because it didn't start as one. It didn't start as a full sideways parabola and then become one. So when there's a restriction on the original, there's restrictions on the inverse. Are they inverses? Are they functions? Is this one-to-one? Yes, because it started out like this. But if you start as a parabola, this was the original one, we just did it. If we start as a parabola, all those points are still going to be there. So the inverse isn't. Okay? So that's something we're going to go really deep into tomorrow. All right? You don't have to graph today. Let's do one more. This is one of our friendly ones. This has a domain and range, let's just make it quick, of all real numbers. Okay? It's a cubic. I'll just tell you what a sketch of this would be. It would be something like this. Okay, we could put it in our calculator and stuff, but again, this is not a graphing lesson. That is this right here. Now let's find the inverse. So g of x, which was y, is now going to become x. And don't forget we have to solve for y. Now, I showed a lot of work in example A. I don't need to see you write +1, okay? Totally fine for you to not show that step. Or show it if you want. Excuse me. Thank you. How do we undo a cube root? Cube. Yeah. Same idea. Same thing as before. You don't have to actually cube that out. And then we just have to subtract the 2, right? So the inverse, that's contagious, is x plus 1 quantity cubed minus 2, right? With a minus 2 there. All right, and if you did make an XY chart, use your graphing calculator, reflect across it, it would look something like this. Terrible graph, but something like that. Like a sideways one, right? The domain and range of this guy would also be all real numbers. It's the same, right? Flip domain range, both going to be all real numbers. Friendly graph, not friendly graph. All right, so we'll get more into the graphing tomorrow. Today you will have to find domain and ranges on some, but you can use your graphing calculator if you need to. You can't really see it. Okay? So find your practice set. 1. And I'm going to kind of get you started here. I skipped number 2 because it's just busy work. It's too easy. If you want to do it, guys, if you want to do it, fine. But like I always say, I'm not here to just give you work, just give you work. If I don't think you need to do it, then I don't give it to you. So if I assign something, it's probably valuable. It is valuable. All right, so this is giving you a function. We're going to graph it. We're going to find the inverse, flipping, and graph that. Okay? So this graph would be 0, -3, 1, -1, 2, 1, 3, 3. Great. There is that graph. I'll get in purple. Next. Inverse, flip them. And graph. What? What's this one? Whoops. That's not it. That's the one. And you can see, even with my not using a ruler or anything, you can see it kind of goes on either side of your identity function of y equals x. Okay, so you can skip number 2. And at the bottom, I'm just going to give you some information to kind of help you start learning these. This is a line, right? This is a line, and when you do the inverse, you're going to get another line, okay? This is a parabola. Who cares what type? Open up, open down, doesn't matter. When you do the inverse, it's going to make a sideways one. Now, you're not graphing these, but I'm trying to have you connect like what the graph would be, because it's just important to kind of know this. This looks like a half of a sideways parabola. When you find the inverse, it'll look like half of a regular parabola. And then, of course, this is another parabola. When you do the inverse of it, it's going to look like this. So find the inverse of each function if it exists. You're going to do the work for all of them, but you should find that these two, you get DNE. Because of what it starts as, it will never be a function when you do the inverse. So start learning those, okay? But the work that you're doing is just switching the x and y and solving for y. So add 5, divide by 2. And guys, you can leave it as a big fat fraction like that, so I call it big fat fraction, or you could separate it out, okay? So you could leave it as x plus 5 over 2, or you can make it x over 2 plus 5 halves, either way. And whatever. Okay, so that should get us started. I mean, as long as you know, like we already talked about, these two don't exist. These two, I guess by default, do exist. Like without doing the work, you should be able to look at these and say, I already know, or you should start getting to that point. Because if you're a parabola, remember we just talked about that? If it starts as a parabola, when you do it. So you look at this and you already know it does not have an inverse. That is a function because it looks like that. So that is just kind of learning that stuff.